Okay, so this is quite a large subject to talk about in 25 minutes, but I'll do my best to cover what happens once you get the HTML and how it actually comes and paints to your page. And you'll understand some of the terms around what's happening behind the scenes as the browser constructs your web page. So thank you for having me in Berlin. It's been a beautiful city. I've been exploring it for the last week. It's been really great to be here. As I was told, I'm Ryan Seddon. I'm a team lead at Zendesk in Melbourne, Australia, where I work on lots of front-end stuff and back-end stuff and write lots of code, but I'm really interested in how the browser works on the front-end side of things. So just a high-level view of what we'll cover. We'll look at sort of the high-level view of like how it comes to be, so how the HTML gets parsed, how the CSS gets parsed, and how it works its way through the different processes in the browser. Then we'll sort of dig into each section, and along the way we'll have some performance insights. So why some performance things are recommended, that can be explained as what the browser is actually doing as it's constructing the website. As I said, this is a kind of like a 30,000-foot view. I've got 25 minutes to cover a really, really in-depth subject, so I'll do my best. So the browser. It's probably one of the most complex applications that we use. I use it for 90% of my interaction with the computer. Like I either have my text editor or I have the browser open. I use all my applications through the browser. So it's a pretty prevalent application, and it's a really complex thing. So looking at sort of like the components that make up a browser for the sort of rendering stuff, you've got the bindings, so that's sort of like operating system stuff. So when it talks to the network, it will use certain APIs for depending on which operating system it's on, so whether that's Mac or Windows. Then there's the rendering part. That's about actually constructing the web page from the HTML that it gets sent to it. There's platform stuff that's dependent on Windows and OS X, so if it needs to do some form controls, there's obviously different stuff between the operating systems. And then there's the JavaScript virtual machine. I'm only going to be covering this bit. So the rendering, so the parsing of the HTML, how it lays out the page, how it actually then paints it to the screen, and you get the final result of the actual web page that you're working on. So if we look at the high-level flow, we've got sort of two processes there. One will pass the HTML, one will pass the CSS. That'll then get combined into what's called the render tree or frame tree, depending on which browser you look at. But they're essentially a data structure of those two bits put together. That'll then lay out that render tree. That means it'll put it in position, so like when you're floating stuff to the left, it'll know to put it on the left. When you have absolute position, it'll know to do all that, and it'll work that out for you. And then painting is the actual operation of drawing the graphics and putting it on the screen, so you get the visual output. So if we dig into parsing, there's a few things about parsing for HTML that are a bit different to most languages. It's very forgiving by nature. You can make a lot of mistakes and it will just work. I think that's one of the great things about web development, is that you can make a lot of mistakes and it'll still work for you. So that means that parsing isn't straightforward. In most languages, if you make a mistake, it'll throw an error and it'll just error out, where HTML will try to recover. It can be halted, so we'll go into when it can stop parsing in certain situations. It'll do speculative parsing. That's kind of a big word, but we'll go into what that means soon. And reentrant, that probably means nothing to you right now, but we'll explain what that means as we go. So there was a stage when we did try to do strict parsing with xhtml strict. But if you made a mistake, you got that error page. That was a pretty bad experience. So if you put something in production that had a mistake, this is what your visitor will see. It'll just take over your whole page and say there's an error in your HTML. And there's also, you can't always control the HTML that's being rendered on your page if you've got like dynamic content, etc. So if we look at valid HTML, this is valid HTML. So you can see I'm missing the HTML tag, I'm missing the head tag. I'm not even closing my tags. I'm not even putting quotes around my attributes. So the parser has to handle this. And you see what it actually outputs in the end once it's taken that in will be that So it'll actually implicitly insert the HTML and the head tags for you. It'll close all the tags, it'll put quotes around attributes. It'll also know how to handle the paragraph from the div. So you see here, if you were to look at that, you'll probably think that the div should be inside the paragraph, but it knows through the rules of parsing that it actually can't do that, so it needs to handle that, so it'll make it a sibling, and it figures that out for you. So it's pretty forgiving in the way that it handles it. So the parsing flow, these are terms common to if you've learned about parsing or not. So there's tokenization, that takes the text, that'll turn it into what's called tokens. That'll then create the parse tree, which will then create the DOM tree, which we all interact with JavaScript. That's the thing that you look at in the browser when you're creating or querying the DOM. That's what you're looking at. And we won't go into the script execution bit, we'll cover that later. So parsing. So as each character comes in through the tokenizer, it'll pick it up. It'll, for example, have special cases for the less than symbol. That'll say that's an open tag. It'll then read the next bunch of characters and say that's the actual tag name. And then it'll look for a closing tag. And then it'll create a token called start tag. And then on the other end, it'll look for a less than / to say that's a closing tag. And that's how it works out where everything's positioned. In the example where I didn't have that, if it finds an open tag and another open tag, it'll automatically close the previous one, depending on certain rules. But that's kind of a simple way. It'll go through each character and figure out the tokens. That'll create a parse tree. So a parse tree is a representation of your HTML. It's pretty much one-to-one. You can see there, it's got all the elements in there, a paragraph, a div, a span. And then they'll take that parse tree and it'll turn it into a DOM tree. So that's all the DOM elements. And that's what you'll interact with the JavaScript in the page. So there's certain situations where I said it will actually stop the parsing of the HTML. So when it hits a script tag, it needs to actually stop, fetch it to the network if it's not an inline script. And then so they'll have to pause. It'll then execute that and then continue on. So if you have that in your page, then it'll actually make it slower to render to the site, to the page. So you get things like network latency, etc. Link and style can also affect it as well. So if the script needs to query information about a DOM element, so it needs to get its height maybe or its width, that can affect the parser and pause it while it's doing that. So there's speculative parsing. So what it will do, the browser won't actually twiddle its thumbs while it's actually pausing for the script to execute, so while it's downloading and executing it. It'll actually create another thread, so another process with the browser, and it'll actually look ahead. So if you've got images or style sheets, it'll actually go ahead and fetch all those before it continues on parsing the page. So it's kind of smart about that. The other weird thing about HTML, if we go back to that diagram, is that it's reentrant. So that means it can be interrupted. So when it gets the script tag, it brings it down. If you do something like document.write, it can actually modify the HTML on the fly. So it needs to go through that process again. So it's not straightforward. So if you download JavaScript and then you do document.write and you insert some elements in the page, it needs to actually be aware of that and then reparse it, redo the tree, recreate the DOM. And so that can slow it down. So that comes to our first performance insight. You may have been told, put your scripts at the bottom, but you've never known why. So now we know that a script tag will actually stop the parser from being able to go through all the HTML and construct a DOM tree. So if we do it at the bottom, then it can go through, it can pass uninterrupted. So it won't need any script tags. It'll go through, it'll create all the DOM elements, it'll create your DOM tree, and then at the end, it'll get all the scripts. And it'll also be faster to render. However, if that's not an option, there are attributes you can use on the script tag. So there's defer. So that's been in IE for a very long time, and now most browsers support it. So defer will actually defer the execution until it's actually done parsing. And async will actually work slightly differently. It'll do a separate thread, and it'll actually parse and execute the script in that thread adjacent to the parsing one. And then the difference between them for the DOM content loaded property, if you're waiting for that, is defer. Defer will stop DOM content loading from actually firing, and async won't. So there's kind of, you can either put it at the bottom, or you can actually put either defer or async on your scripts. It's kind of a trade-off between them. So this is parsing sort of visualized in the form of a GIF. So this is kind of like my first website, what the parser looks like. So you can see it's quite vivid. It never actually quite falls over. It's trying to figure out what the hell are you doing with that div tag. And then you can sort of see at the end, he just chucks the spade. That's kind of like, there's your website. I thought that was pretty good. CSS parsing, I'm not really going to say much about CSS parsing. It's pretty standard in the way it works. If you've ever done parsing in any other languages, there's nothing special about it. It'll create what's called the CSS object model. So like the DOM, we've got the document object model, we've got the CSS object model. Basically, that's a representation of your styles. You've got a style sheet, you've got rules, you've got selectors, declarations, and so on. So that'll then move on to our second stage of combining those two. So we've got a DOM, we've got a CSS object model, and that'll go into and create what's called the render or the frame tree. So that's the combination. So you combine the two object models. It'll do style resolution, so that means it'll figure out all the styles applied to nodes. It's the actual representation of what will show on the screen, and it's not a one-to-one mapping of your HTML. And we'll explain what that means in a second. So if we revisit that diagram, you can see that parsing HTML and CSS isn't always necessarily can happen in parallel. JavaScript can affect those two running at the same time. So the render tree is actually multiple trees. So there's like 4 of them. There's the render objects, which are kind of like the actual node itself. So it's got a reference to the DOM node. Hanging off that, the render styles. So that's kind of like the styles that apply to that DOM element. You've got things like layers. So the browser needs to know about if this object is position absolute, or if it's got a z-index on it, it needs to know how to actually place it on the page, so it puts it in the correct order. And then there's line boxes, so that's handling text. So if you've got wrapping text, it needs to know how to lay out that as well, based on font size, etc., the constraints of what it's inside. It gets a bit complex. So like I said, it's not a one-to-one mapping, so things that are not in the render tree are all non-visual elements. So your head, your scripts, your titles, any node that's actually hidden by display none, or any nodes that have a parent that's hidden by display none, won't actually make it into the render tree because it doesn't need to show up on the page. So if we look at things that are in the render tree but not in the DOM, so this is quite a lot of text to look at, but we can look at the top. We've got a paragraph tag. So we've got just a sentence, and we've got 2 inline tags with a strong and the emphasize tag. On the left-hand side, down the bottom there, you can see that's actually what the render tree looks like. It's got a render block, which is assigned to the tag. That's a block level element. Inside there, it's got a text. Then it hits the strong tag. Inside that, it's got some text, emphasize, and so on and so on. Hanging off that render block is the line boxes. So that will figure out based on the constraints of where it's rendering. So if it needs to wrap the text, it'll actually create a line box, which is like a box around each line of text. So if you can imagine like the quick brown fox was one line and jumps over the lazy dog was a second line, that'd be 2 separate line boxes. So on the right-hand side there, you can see there it's got like line box. And so that knows how to lay it out, and that'll actually change based on if you change the width of an element or if you change the browser, that'll need to figure out what's now in different lines. So the DOM node, like I said, is converted to render object, or the render object has a reference to the DOM node. So this is the visual output of what gets shown on the page. It has geometric information about it, so its width, its height. It can then lay out and paint itself, so it'll work out where it sits on the page in relation to everything else that it's sitting with. So if it's floating, it needs to obviously have multiple elements. If it's got to float it before it, it'll need to sit next to it. If it's position absolute, it's taken out of the flow and positioned based on like if a parent has position relative, for example. And it'll hold styles and computed metrics about itself. So it'll hold its font size, its width, its height. So hopefully this will work. This is a really cool video of if it loads. Someone hacked the Mozilla Firefox and actually drew boxes around as it's laying out a page. So this is obviously slowed down quite a lot, but you can see it's actually figuring out dimensions. You can see it's laying out all its children and it's figuring out its position. So you can see it starts at the top left of its box and then it works out where it needs to sit. I'll play that again. But it's quite cool. You can see it actually has to do quite a lot of work. It'll lay out all its children and then it'll figure out where it is. So you can see it starts there and it slides down. And this is not a very complex website, so you can imagine something that's got quite a lot of stuff going on that needs to do quite a lot of work. But I always like watching this, it's really cool. So how it lays out all that information is it calculates all the visual properties. So it'll have to combine all the styles. So that means the browser default styles, the external styles that you're linking to, any inline style elements or any inline styles. It'll also take into account some of the old HTML element properties, attributes, so like BG color. It'll have to take that into account to know to set a background color if that's on there as well. There's a lot of complexity around matching rules for each element, which I won't go into because it's quite a big subject, and how it shares the styles and how it does the cascade and all those sort of rules around how CSS works. And it'll do the style computation, so it'll work out information about it, so colors to apply, width and height, etc. Right, so now we're into the layout process. So we've got our render tree of our visual information, and now we're going to actually lay it out. So like that video showed where you can see all the elements moving around the page, that'll actually lay it out now. So this is the process. You might have heard it called reflow or relayout as well. There's a few terms for it. So it's a recursive process. Hopefully you remember what recursion is. So it'll work its way down the tree. And then if we remember, each render object that's assigned to a DOM node knows how to lay it out itself. So then it'll actually lay out its children first because it needs to know, based on all the dimensions of the children, what height and what width it should be. So it'll lay out its children and then it'll lay out itself, and then that'll actually flow all the way through the tree of your render tree and then figure out where everything sits. It'll batch layouts, so it'll do incremental layouts. So the browser will be intelligent and it won't, every time you do a change, it'll do a relayout. It'll actually try to combine them all and do them at a regular interval. So essentially when something changes in the DOM, the render tree representation will say, flag itself as dirty, so it's saying, I need a relayout, so you need to actually do it. So the browser will come along and pick up all the objects that need layout, and it'll lay them all out in one go rather than individually. So that'll traverse the tree using recursion, and then it'll find all the dirty render objects, and then go, okay, I need to lay out all these bits and figure out where everything sits. And this will happen asynchronously, so it won't block. However, there is also immediate layout. So in certain situations where it needs to lay out the entire document, for example, if you change the font size, so if you have a fallback font and then you have a font face come in and obviously the height of the font might change slightly, that'll actually cause a whole layout of the page because it needs to figure out where everything sits again because it shifts down. That'll also happen when you resize the browser and also when you access certain JavaScript properties like node offset height. So if you want to get the height of an element, it needs to actually lay out to actually give you the proper value. So that comes to our performance insight number 2. So we want to take note from the browser and we want to batch our changes. So when I act like the browser, you want to do all your DOM changes in one go rather than like read, write, read, write, read, write. So you want to do all your reads in one pass, you want to do all your writes. And we'll just show here a bad example. So this code is trying to create like a aspect ratio for a div, so like a 16:9. So it's reading its width and it's dividing it by 1.7 and it's going to get the height, so you get like the 16:9 resolution. So you can see here I'm reading the client width and then I'm writing it to the DOM. And then I'm reading it and then I'm writing it. So what that forces it to do, because I'm reading it and I'm writing it, that's fine, but then I read it again, it's like, oh crap, I need to actually lay out the page. And I need to give you the true dimensions for the client width because div 2 could have changed. Because of div 1 is got a different height now, so that could affect div 2. So it needs to actually go and lay out the page and give you the correct value. So the best way to do that is actually to do your reads in one go and your writes in one go. So you want to actually read all the values back, and then you want to write them in one go. So this is obviously naive code. So the real-world situation is there's a library, if you're not using a framework, called FastSOM, which is pretty good. They've got a really good article called Preventing Layout Thrashing, which talks about exactly like reading, writing, which I highly recommend you read. So FastSOM will actually give you an API to do all your reads. So you call like fastSOM.read when you want to read something from the DOM, and likewise you do write, and that'll coordinate the process for you. So it'll make sure it'll batch all the reads, and then it'll do all the writes one after the other. And most modern JS frameworks will do this internally. So React definitely does this, and so does Ember with their newer rendering engine. So finally, we are onto for paint. So this is actually what takes all the information from the render tree, and it'll actually do the calls to actually paint something. So you kind of think of it like the Canvas API, where you're drawing boxes. Painting is this process of taking all that information from the render tree and giving you the visual output. So there's a few things about it. It will take, so it will lay out the render tree, so it'll take all that information. So you've done the layout, so it knows where it sits, the coordinates of the items. It'll create layers. So layers are things, if you've got a position absolute and you've got a high Z index, it needs to actually make that come first. So it'll actually paint from the bottom up. It'll work its way up so things are displayed correctly. It's an incremental process, and it actually is a 12-step phase. So that means it needs to like paint like the background color and the background image and the borders and the shadows, etc. It needs to build it up so it comes out in the correct order and you've got the correct rendering. It's quite a heavy process. So if we remember one of the trees off the render trees or render layers, it will try to group things into layers. So if you've got a position absolute element and all its children will be in its own layer. If it's got transparency, if it's got overflow hidden, if it's a canvas or a video, it'll put it into its own layer. And it's kind of a many-to-one relationship. So one layer can have many render objects or many DOM nodes that it can put onto the screen. Painting. So painting it produces what's called a bitmap for each layer. So this used to be CPU-based, but a lot of browsers now will do it on the graphics card, so on the GPU. So that's a lot faster. The GPU is obviously made for drawing graphics, and it makes sense. There's some really good articles about how, especially like Blink and WebKit do it, and how they sort of speed up their performance of the painting performance. So it'll take that bitmap, which is just like a JPEG. It'll upload it to the GPU and create what's called a texture. And then those textures will be composited into a final image. And that's what actually gets displayed on the screen. It's not actually individual bits. It's just like kind of like a bunch of images that get put together and put on the screen. So this comes to performance insight number 3. So inlining critical CSS. This is kind of like a new thing you might have seen. Essentially, it's a way of taking the most important bits of your site and inlining the CSS in a style tag inside your HTML right in the head. And what that does is that'll speed up first paint times. So you kind of delay everything else. You delay all your other CSS, all your other JavaScript. So then the browser can come in, it can parse all your HTML, and you can get something on the screen really fast. And you'll see a lot of sites like Filament Group and a lot of people who are really into performance talk about this a lot. And the last bit about delta last bitmap. So browsers can have a performance thing where they can compare the last paint to the next paint, and they can do a diff, kind of like when you do visual regression testing in your web apps. They can kind of do something similar where they go, okay, well, only this bit changed, so I only have to draw like this box here. It can be kind of smart about it. So we take an example. I don't actually do this on my website, but I just went into the dev tools and hid stuff. This is my blog. So the idea is that on the first render, I would get this. Essentially, the most important thing of a blog is the blog content. You don't care about related articles or my logo or the blog title. You just want to read the article. So the idea is that you render that straight away. And then on the second pass, when everything loads asynchronously, you kind of get everything else coming in. So you can see there, like, I've got a different font that comes in, so that's like Helvetica by default, and then it comes in and uses the Ubuntu font face, and it loads everything else. So the idea is that you could get that in under a second. You could have that on the user's screen. So it gives them the illusion that your site is really fast, but what you're doing is you're delaying a lot of the stuff, and you're just giving them the important information. And I guess the other thing is to think about is that you don't want stuff to shift around. So like the header up the top, you want to have a fixed height. So in that inline CSS, it doesn't like jump. And you kind of want to make it not jump as much, so like it's not jarring to the user. So all of these steps that I've talked about apply after page load as well. So this is obviously the process to get it onto the page initially, but things like layout and paint all happen as you're interacting with the website. So it's really important information to know about. So for recap, we pass our CSS and our HTML. That creates a DOM tree. The DOM tree then gets converted into a render tree. So the CSS and the HTML are combined. It's actually 4 trees. So we've got the layers, the line boxes, the render objects, and the render styles. So layout is a process where it computes where the elements will appear on the page based on its relationship to other elements, taking into account all the CSS. And then painting will actually produce an image of that layout and give you the visual output that you're expecting on the page. So like I said, this process is really complicated. I've only scratched the surface. There's some really great articles here that I'll share around later. I highly recommend you check it out. There's a few good talks in here. And there's a really good article about going more into in-depth of how the browser works as well. So the moral of the story is go hug a browser engineer. They have a hard job. It's quite a journey for me to discover all this information, let alone know how to build it all. It was really interesting, and it's made me a better developer, I think, to understand how it all works. Thank you.